and generally more so the theory than the code, but we'll be touching on some code as well. And I will try to leave lots of time at the end for questions as well. I would assume a good amount of you are maybe working on the stock prediction challenge, although maybe not all of you. So I just wanted to start us off by asking if you would introduce yourself, if you feel so inclined, and what challenge you're working on and how it's going.
Hi, I'm Joseph. I'm working on the stock market challenge.
I guess I'll go next. My name is Syed Rizvi. I'm also working on the stock challenge. I'm looking at several approaches, but I'm excited to learn more about reinforcement learning.
Hi, I'm Ahmed. I'm also working on the stock prediction challenge.
Hi, I'm Rafi, and I'm also working on the stock trading challenge with Ahmed and Syed.
Hi, I'm Miguel, and I'm also working on the stock prediction challenge.
Cool. All right. Well, seems like we have a pretty homogenous group here, although I don't assume everyone's working on the stock challenge. That's fine. Reinforcement learning is just a really exciting field. I guess it's more recent for me. I mean, it's a more recent field in general. I guess at the beginning of last year, I didn't know what reinforcement learning exists, and I learned about it in a class, and one thing led to another, and ended up doing an internship using reinforcement learning this summer, which was just really interesting, and just found out how powerful the method is, and got to look more into just the math behind it and the most up-to-date research papers, and that's kind of what I hope to share with you today, and also tie it to practicals as far as, I mean, probably most of you are thinking, how is this going to help my reinforcement or my stock prediction challenge? So I'll try to talk about that too. All right. Well, reinforcement learning, the broadest kind of paintbrush I could give to it is that I always thought there's two forms of machine learning: unsupervised and supervised. And supervised is where we have a bunch of observations that have features and a target, and we fit some sort of model to predict the target given the features. And then there's unsupervised, where we don't have a target variable, but we still try to do some sort of extract some sort of information from the data, and that might be through dimension reduction or clustering. But I actually didn't know until recently that there was a third form of machine learning called reinforcement learning, which doesn't perfectly fit into either one of those paradigms. And in a lot of ways, to me, it seems like it's the closest we have to actually like how humans learn. And indeed, reinforcement learning is built on psychology, the theory of reinforcement learning in psychology, that says that humans are really just trying to optimize an internal reward function that we have in how we operate in the world. And as babies, we start learning, we kind of have an inbuilt reward function, and we start learning, hey, as babies, this action, when I'm in this state and I take this action, it causes me pain. When I'm sitting on a high chair and I decide to jump off, it causes me pain. When I am playing with another baby, and that's my state, and I give them something, then they smile, and that makes me feel good. So that gives me a reward. And so I start learning that in different states, if I take different actions, that will maximize my reward. And also, I can't always just take whatever maximizes my happiness in the current moment, because ultimately all of us want to maximize happiness or reward, however we define that, in the long run, right? And so if we just tried to always do what was made us most happy in the moment, that would be called like a greedy approach. the fact that you are here at 9:40 p.m. learning about a pretty technical concept probably means that you're looking to maximize some long-term reward rather than just your instantaneous reward, where you could be, out doing enjoying your Saturday night with something a little bit less technical. And so even though this is maybe bringing you more pain than reward right now, over the long run, it will give you a long-term reward. So just keep that in your mind. It should be an intuitive concept to us. Indeed, it was based off of psychological research. So it explains how us as humans work. And the whole field of reinforcement learning in machine learning is just how do we formalize that into a way that computers understand, which is always through math. Now, let's see, I'll share my screen to move on. Where is it? And so I'm going to be talking through this notebook. All right, well, first let's talk about something called an environment, which formally is actually called a Markov decision process, which involves a tuple of a state space, action space, reward function, and transition function. And so our life can be kind of described as a Markov decision process, where we have in our life, the state space is very large. It's whatever space we need, features we need to explain the state we're in at any moment. So in a very simplified state space, maybe our state space would be our space-time dimension. I'm at this point in my life, I'm at this Latin lawn on the world, so that defines my state space. But of course, with the human life, it's much more complex. But that's a general idea. And then the action space is all the possible actions I can take. Again, as a human, that's just intractably complex. But I'd say in the simplicity, maybe I can walk forward, move left, right, or backwards. And so that would be an action space. Now that's actually a discrete action space. And then the reward function is a function that maps from the state, I guess I should actually, yeah, it maps from the state action space to a real number. And so that it's a reward, the reward function is a function that takes a state I'm in and an action I take, and then returns the reward I got for taking the action in that state. And the transition function is what the world gives back to us when we take an action. So remember, like as a kid, we start kind of understanding this transition function where we give a toy to another person, and in turn, that probably means that they're going to give a toy back to us. But note that T is often a stochastic or probabilistic model. When we give a toy to someone else, we don't know for sure that they're going to give a toy back to us, but that increases their odds. But often, the transition function in the world is so complex that we can't actually directly model the probability distribution over all possible state actions pairs. And so reinforcement learning, where it really shines, is that it's able to interact in a world where we don't actually perfectly know the transition function T. We may be able to query T by acting in the world, but we don't know beforehand, before we actually act in the world, what state we're going to get back. So, as a baby, we don't really know exactly what's going to happen when we give a toy to another human being, but we can still act in the world, and we can still try to maximize the reward function, even if we don't explicitly know beforehand the probability that the other human will give us a toy back. All right, so let's maybe formalize it just a little bit more. So here's what we call we've been talking about humans, we would call ourselves agents. Agents are objects that can take an action in an environment. And so they are equipped with actions that they can take in our action space. And when they take an action in the environment, that they take a step, we say a step in the environment. And then the environment returns the reward we got for taking that step and the next state that we're in. So in this case, there's a dinosaur trying to make it through a maze. And perhaps we would give a reward of 0 for crashing, or maybe -1 for crashing into a wall, and a reward of 1 for not crashing into a wall. And so the dinosaur should hopefully learn to take steps in directions which make it not crash into a wall. And so in this case, what would a good state space be for this example? That's a question anyone can speak up.
Moving down.
Okay, so that you just mentioned probably the optimal action the dinosaur could take right now, but that's not quite the state space. Oh, I think I have some messages in the chat. No, this is me maximizing my short-term reward. I feel you. Okay, and then what does it say? Can you share the link? Yes, I can. Let me do that. Actually, I think I already have it copied. Okay, so the someone's an answer at this a state. So the answer to what is a state space? A state for each square in the maze. Close, maybe that could be correct, but we want to give us the state space should be kind of relative to where the dinosaur is now. Remember, like state space for me wouldn't be the map of the entire world. It would be my current lat long and say the time of my life. Okay, distance from the walls on all 4 directions. Yes, that is the correct answer. So in maybe the most simple answer, the state space would be a 4-dimensional discrete space that would be, you know, is there a, maybe it would be a 0, 1 vector where each entry in the 0, 1 vector would be 1 if there is a wall in the respective entry and 0 if not. So in this case, the dinosaur has a wall on his left and right side. And so, you know, depending on how we encode that into a state space, which is up to us as engineers, that might be, you know, a vector 1, 0, 1, 0, meaning they have a wall on the left, not on the top, on the right, but not on the bottom. And as we're just picking the state space, it's a very important engineering decision. Most of my research this summer has been, how do we define a good state space? I mean, it can make all the difference. The state space should be a good indicator to the agent about what action to take. So if I just tell the dinosaur what the time in Tokyo is, that's not going to be very useful to the dinosaur for it to know what action to take. So state space should accurately describe what, should help it know what action to take. Okay, so then once it takes an action in the environment, it's returned a reward and a state, a next state. So if I said down, then the next state would be where it would be, I guess, 1, 0, 0, 1, because there would, if it moved down, then it would now have a wall on its left, but not the top, or not the right, but on its bottom. All right. Now we still haven't talked about if this agent is dumb or smart, or how it acts, but we've just talked about, look, an agent can take an action in the environment, and when it does take an action, it gets a reward and state. So what we should probably talk about next is, well, how does it know what action to take? I guess before we move on to that, let's try to just implement with some examples an environment. So even though this is a very young field, very thankfully, someone, well actually OpenAI, has standardized the interface to an environment. And this makes it really easy to kind of create new environments because there's just been a very clean interface created. But if we just, and it should be intuitive too, based on what we've talked about so far. If an environment, we should have like an initialization function method when we're defining an environment that says, hey, what's the action space and what's the state space? And then we should probably have like a reset method that resets the dinosaur back at the beginning of the maze. We should have a step method, which is what we've talked about. The step method should take an action and then return the reward and state from the environment. Okay. So I guess the step function, I should say here, it should also return a reward. And then the reward function, which takes in a state and action and returns a real value, and an observation function, which returns, where it returns an entry in the state space that's relative to where the dinosaur is right now. So it might be that 1010 if there's a wall on the left and right. And then this done signal should indicate if the agent has moved into a terminal state in the environment. And so maybe here a terminal state might be exiting the maze completely. That would probably be a bad terminal state. Or maybe finding the tree, which would be probably a positive terminal state. But in either case, the done function would want to be return true when the dinosaur enters either of these states. So I'm going to switch examples on you and talk through code a little bit. So think of another game, which is a very simple game, and it's called a balance beam game. And just imagine a rod on a balance beam, and we can add weights either to the left or right side of the balance beam. And the goal is to add as much weight as possible without tipping the balance beam. And so we've probably already thought, hey, that's easy to solve. Just make sure, well, you have some tolerance for how much weight you could add on one side before the balance beam becomes completely tipped, right? And so maybe a good rule-based algorithm would be like, okay, add one weight on the left side and then add a weight on the right side and then one on the left side and one on the right side and so on, so that it's never too unbalanced. You wouldn't want to add like to the left side, to the left side, to the left side, because in the balance beam would completely tip. Okay, so obviously this is a very oversimplification. We could create a rule-based algorithm that would do it just fine. But just to show you how the environment gets set up, that's the most important thing I'm showing you here. So whenever you create a gym environment, you need to inherit from gym.mv and just import gym. If you don't have gym, you can pick install gym. And then you define a state space. So gym comes with two spaces that So it comes with a box space and a discrete space. So for how much weight, so say we could add any amount of weight to either side. We're gonna define the state space, and I'll show you later, as the left weight minus the right weight. And so this could, I guess, be a continuous measurement, right? But it's a one-dimensional continuous measurement. It's the amount of difference in weight. And so that's why, so for continuous measurements, we use a box. And then what's the action space on this? Well, the action space is we could either put a weight on the left or the right. This is a discrete decision. So that's why we say discrete and with a 2 in here, because there's 2 decisions we can make. The box space is, well, why do we say it's, so remember there's a tolerance that we can be within before the balance beam tips. And so maybe that's like 1 weight unit between the 2 sides of the balance beam. And so the state space will actually, if there's a difference more than that tolerance, then what will happen is we'll declare we're done. It failed, right? And so if the absolute observation, which is this, is greater than the tolerance, we'll be done. And so that's why we use negative tolerance to tolerance, because this should be the extent of our box, of our state space. We shouldn't observe differences greater than negative tolerance or tolerance, because if there was a difference that big, then the balance beam would have already been tipped. So when you define a box, you define the limits of the box. All right, and then there's a reset function. So remember, we talked before about how a reset function might like put the dinosaur back at the beginning of the maze. For us, it kind of resets this balance beam, so removes all the weight, you could say. And then we define like an observe function that just returns the, and so this is like the instance in a state space. And so remember, whatever we define as our state space should be informative to the agent. And we haven't talked about the agent yet, but whatever we return to the agent, and think you could think of yourself as an agent. If you wanted to know what action I should take of left or right, you should know like, well, how is the beam balanced right now? Is there negative weight to the right or positive weight to the left? And so that's what we're going to return as our observation. The reward function, just it's a very simple reward function. It returns -1 if we're done, because if we're done, that means we failed. And otherwise, we return 1, meaning that, you know, it's a positive reward. We are able, we chose a good placement of a weight. All right, so now the step function, which we talked about above, it takes in an action. So in this case, the action could either equal left or right. And then it pretty much, words are hard at this time of night, but it gives the action to the environment, and then the environment pretty much updates the state. And so in this case, how we implement that is the environment, or like the state, the environment is, you know, the left or the balance beam. And so if we said, okay, put a weight on the left, then the weight in the left grows by 1. If we say weight on the right, then the weight on the right grows by 1. And then we calculate the reward. And for a gym environment, we always return these 4 elements in this order. It's very important. We return the observation, which has to exist inside the state space. We return a reward, which should be a real number, a scalar, real number, a done signal, which should return true or false. And then this is any other extra information, which should always be a dictionary, but in our case, we don't have any extra information. We could put something there, but it doesn't matter for the algorithm. That's just for like maybe humans that want to read out more information. And then we just define a render that kind of tells us, okay, what state is the environment in right now? Any questions? Well, okay, let me just, before I open up to questions. So how then we instantiate the balance environment, we reset it and get the observation from resetting it. And then we render, which should print out the left and right. And so we see that when we reset it and then render it, we can see that it is properly reset. There's no weight on the left or right. And then we take a step in the environment. And in this case, we step left, meaning we put a weight on the left. And we can see here that once we've taken that step, we can print out the imbalance observation, the reward, and the done signal. So in this case, the done is false, which means we didn't tip the balance beam. So we got a positive reward, and there's a positive imbalance right now. And then if we take another step on the left, now the weight difference is beyond our tolerance. And so what you can see is we have a done of true, and we have a reward of -1, which means that, remember, we defined that reward because we failed. And so we have the imbalance of 2. So at this point, we should reset our environment and try again. Okay. In this case, we call this up to the point that we are done. We call that an episode. And so we can get the total reward or episode reward by just adding together all the rewards for the episode. So in this case, you know, so I was the agent because I hard-coded the left and left. And I was kind of a dumb agent, you know, that probably wasn't a good decision. And so my total episode reward for doing that was altogether 0, because I got 1 point, but then I lost. Now, if I had put left, right, and then left, left, then I think I would have had like 3 points. So I would have been a better agent. So my reward that I get defines how good of an agent I am. But pretty soon we're going to start talking more formally about the agent. So someone shout this out or put it in the group chat. In it, the answer to this question. In a gym environment, a box represents a blank space, meaning that there are blank elements in the space. So the answers are continuous and infinite, discrete and finite, continuous and finite, or discrete and infinite. Anyone want to take a shot? All right, everyone needs to drink a Red Bull right now. All right, we have an answer, continuous and infinite. You are correct. A box space is continuous, and it's kind of the telltale is that there's two spaces, a box space and a discrete space. So that must mean the box space is continuous because the discrete space is discrete. And in a continuous space, there are infinite number of possibilities. So that's going to be important as we move into what agent we're able to choose. Yeah, the correct answer to that is continuous and infinite. All right, anyone else have any questions about environments? Whether informally in the code and like, you know, if you want to ask any questions about the code, or formally in like the notation. Can some people please either put it on the group chat or privately message me if tell me if this is going too fast or going too slow or just right. If just like 3 or 4 or 5 people could message me that, and hopefully it's a representative sample, then that would really help me know. I've had 2 people message me, thank you. All right. 3 people. No peer pressure, answer what you need. Okay. All right.
There was also like a question earlier that was like, how are infinite elements represented in computer memory?
Yeah, infinite elements represented in computer memory. I mean, an infinite element is just like a number, right? A real number is an infinite element. It has infinite many settings. So, I mean, your computer has no problem storing a real number, like 5, right? So, yeah, it doesn't mean that it has infinite dimensions. That would be I'm not talking about that. I'm just saying that it has a finite number of dimensions, and a continuous space has infinite number of settings for that, for a set number of dimensions. Okay. All right. And I did have a couple people message me privately that maybe it's going a little fast. So if you're feeling like that too, you know, don't feel bad about yourself. I understand, you know, everyone's at different kind of levels coming into this, and so feel free to message me afterwards, and I would be happy to explain topics more in depth. I have all night, but it seems like there's a somewhat symmetric distribution right now, so I will continue. All right. So we're going to move on to the agent. So far, we've mostly talked about the environment. And we've said, you know, a dinosaur can take these actions, but we haven't talked about the brain of the dinosaur. How is a dinosaur going to know what action to take given a state? And that is the $1 million question. Well, there's going to be a lot of $1 million questions, but there's a lot of money to be had in reinforcement learning. So the first $1 million question is, how does the agent come up with a good, what we call policy So a policy is the mapping, the function that maps in its state to an action. So that's a formal way of saying the dinosaur sees where it is in the state, and it has to decide what action to take. So the policy maps the state to the action. And a good policy is one that comes up with good actions for the current state. And how do we define good actions? Well, it's going to be one that maximizes the long-term reward. All right. So we often use the symbol pi to represent the policy function. That's just kind of a convention, an accepted convention of reinforcement learning. And so pi is a function that maps the state space to the action space. So it's going to map a state to an action. So I operated as the, or I guess I was the agent that, according to my policy, and maybe it wasn't a very good policy, decided to choose left and left. And giving, you know, I saw, okay, my imbalance is 1, so I'm going to choose left again. And you're like, why did you do that? You're right, that was not a good policy. That was probably not a good action to take in the current state. But you know what, I did it, and I'm sticking with it. But let's talk about, what if we can make a rule-based agent? So as soon as we all saw that problem, we quickly thought, okay, like this is simple, right? Like if we're balanced on the left, then we need to add weight on the right. And if we're balanced on the right, then we need to add weight on the left. Okay, simple rule-based algorithm. So this is something I'd really say, even after like practically from researching for an entire summer, and I'm still researching in this space, is I think one of the mistakes I made going into this was I just jumped in with, okay, I got my environment, and now I'm gonna try to build this really advanced policy that's like uses deep neural networks and everything and advanced techniques. And the problem, I mean, just it makes you pull your hair out with deep learning stuff, is that it's really hard to debug. Because deep learning is probabilistic, it's, you know, you could rerun your tests and each time come out with a different result and not really know why. And the deep neural network is very, I mean, it's deep, so it has like a lot of parameters, and it's just you can't like print it out, you know. So it's like very hard to know why your overall system is failing. And so if I would go back, something I'd tell myself is to start with the smartest rule-based system I could think of, and then to build off from that. Because at least with a rule-based, it might not be the best policy, but you know, it's deterministic. So we can look at it and think, and like see, is our reward function doing what it should be doing? Is our state, you know, giving us the observations we would expect? And so just from a kind of software development point of view, I try to build a rule-based policy first. So a rule agent, or just an agent in general, is just, we represent as an object which is equipped with a policy method that takes in a state and returns an action. Okay, and in our case, the state is simple. The state, remember, represents the imbalance. And so if the imbalance is greater than 1, then return right, and less than 1, return left. Okay, now we can instantiate an agent, and then remember how we instantiate an environment, reset it, and then we're going to print it, and then we're going to take our first step in the environment. So we're going to use our agent policy to map the observation from our environment to an action. And then we're going to print that action. And then, so now our policy has said, I want to do this. And then we're going to actually carry out that action by stepping in the environment. And remember that step function returns an observation, a reward, a done signal, and that information, which we don't use. So we just use an underscore. Okay, so let's see what happens. Yes, I shouldn't have done that. I have to go back and all right. So you can see now that, let's look. So when we first printed out the environment, it had 0 weight on its left and right. And then we decided to take action 0, which, you know, honestly, I don't redefine that all the way at the top. I think that is left, okay? So 0 represents the left. So we decided to put a weight on the left, and then we could see that, you know what, we took the action and the environment returned weight on the left. And then so now we have this observation, and that's what we get from this observation. And so then we feed that observation back into our agent policy, and the agent's policy, based on this rule-based system, is able to say, hey, you have too much weight on the left. Let me choose an action which puts weight on the right. And so here you can see under step 2 that I decided to put weight on the right. And so now we are balanced again. Hooray. And then this rule-based algorithm, you know, does what any common sense person would do. It would add 1 on the left and then 1 on the right, and so on and so on. And according to this rule, it would actually, I mean, it's a perfect policy. So it would go on. This is the optimal policy. It would be able to carry out to infinite. It would actually be able to like get infinite reward, which in cases like this, in practice, we probably want to put a limit on the number of steps we can take in the environment, because we're going to start having exploding numbers because we're just going to, like, you know, go to infinity. So we normally want to put like a limit on the environment. All right. So the $1 million question, like I said, is how do we find an optimal policy? And so let's just go through some of the, for perhaps if you like notation and it makes sense to you to go through the notation, let's do that. Okay, formally, the goal of reinforcement learning is to learn an optimal policy pi. I guess I should actually say pi hat here. Well, I'll show it later. An optimal policy pi, which can be stochastic, parameterized by some parameters theta. And if you don't know what I mean by like parameterized by like some theta vector, you should probably go back and watch my machine learning theory where I talk about what that means. But anyway, so our function pi is parameterized by theta, and it maps a state or observation S into the observation space to an action in the action space. And so we can denote all of that together as the policy pi with parameterized by theta gives some action with given some state. And yes, this notation is actually more commonly used with like probability. This notation, we might read it as the policy pi returns the probability of taking some action given some state. And that is, sometimes we would like to represent pi as not a deterministic policy, but actually as a probabilistic policy, just for theoretical reasons. When pi is optimized, we denote it pi star, which is just common nomenclature for the optimized version of something, which is actually shorthand for pi when it's equipped with the optimal parameters, theta star. And so if you've done any machine learning, you can start to see that our goal would be to find that theta star, or at least some approximation of it. In deep RL, theta are the weights to a neural network. Unlike supervised learning, RL does not require any labeled training data. Instead, RL interacts with the environment by being presented with some state, choosing some action according to its policy pi. Under the assumption of full observability, which is, you know, like the dinosaur can view everything the dinosaur needs to view at all times, which is all we're going to be talking about here. RL operates on the premise that the environment can be viewed as a Markov decision process with a possibly stochastic transition function. And that's, we've talked about this. The environment returns a reward and a binary signal done. The process of observing state S, getting action A, according to the policy pi, and executing A in the environment is called a step. So we've looked at that, right? The reinforcement algorithm works to find the policy parameterization that maximizes the expected reward over the episode. So formally, this is what we'd like to do. We'd like to find the argmax of theta, which maximizes the expected reward of all S and T's where or S and A's, where actions come from our policy and the states come from this transition function of the environment. I know that's pretty heavy notation, but yeah, I mean, hopefully the intuition that we've built up so far has kind of, you can use that to understand this equation. It's similar, you know, for our life, we want to maximize, we want to find the parameters, you know, I guess we could think of this as like the neurons in our brain, or the thought processes that happen in our brain that we want to find. We want to, you know, you always hear like think positive thoughts. So we want to find the, like, so think of theta as like the thoughts we have, and or like the parameters of our brain that, I guess, create the thoughts, whatever. So we want to find like the best thoughts that we can have that maximize the expected reward over all of our life when we take actions with respect to the policy that, you know, that the way that we operate in this world, given our thoughts and the state that we're presented with. And I don't mean to get too philosophical. I'm going through ethics right now, and I guess theta could also be thought of in the Kantian sense as your will, your willpower, your will that, and so you take some actions according to, you know, how you will, and you want to mold your will to generate the optimal action. Sorry, I don't mean to get too philosophical. I'll stick with the math. And then the states come from, you know, the world. We don't get to control the states that we have, but given some state that we're in and some action that we take, the world gives us back the next state, the next day. It gives us back tomorrow. All right. So the new $1 million question is, how do we optimize theta? And Felicia, I have till 11. Is that correct?
Yes.
Okay, sweet. How do we optimize theta? How do we come up with this optimal parameter for a model, or, you know, optimal willpower or optimal thought process? So we're going to talk about that, and we're going to talk about two methods that do that. And so in this entire lecture, though, we're only going to be talking about model-free learning algorithms, simply meaning that we don't assume we know the function t. You know, we can, like in our life, like I guess one way to approach our life is to try to figure out exactly what tomorrow will bring if we take an action in our current state. And then we're trying to like figure out the model, you know, like, what if I just sat here right now and just thought of all the possible states I could be in, and all the possible actions I could take, and how that would affect my day tomorrow. And then I'd be trying to build like a model in my own brain. But in model-free algorithms, we don't explicitly try to build that model. We try to just operate in this world by, you know, by taking actions that that seem good in the current like state that we're in. That's, I think, how most of us. I mean, actually, it's to be debated. It seems like humans kind of have a mixture of model and model-free and model-based. You know, it seems like a lot of times we just go through life and we take actions without really like fully thinking through the long-term effect. But sometimes we do build models in our own brain and try to predict what that will bring for us. Anyways, again, sorry not to get too philosophical. Yeah, in model-free algorithms, we don't assume that we know exactly what that t function is. So the first method that I learned about, and I think is the most, or I think is most intuitive to me, I guess simply because it's a little bit simpler in the math, is using a Q function. So Q functions are often, not all the time, but often off policy. And so I'll talk a little bit about what that means. If you start looking into reinforcement literature, you're going to hear a lot of model-free and off policy. So I wanted to give you a little bit of knowledge about what that means. But I'm going to explain the basic premise of the Q function. Q function is a basic form of machine learning, or reinforcement learning, which uses Q values to iteratively improve the behavior of the learning agent. What is a Q value? So Q values are defined for states and actions. So you could think of them as a function, or we also, in the most basic way, we actually build like a matrix, and then like the S and A are like indexes into that matrix. And so we can actually query for what is the Q function at some state in action. And what it's supposed to be in the end is an estimation of how good is it to take action A at state S. So this how good is it is how much reward do we expect to get, like long-term reward. And so maybe we try to build a Q function in our own mind by going to this class. We have some idea of how much value it's going to bring us in the rest of our life, and we probably don't actually have a perfect idea of how much value going to a good class will bring us, right? So we're going to talk about how do you update that Q function. So in our own brain, we have an idea of, given the state that I'm in, I'm tired and I just want to relax, but I'm going to take the action of going to this workshop because I believe that that's going to have some given reward over the rest of my life. And what might happen is I have some idea that say I could quantify with some number, but then in a week I find out that, and this is kind of what happened to me. I was learning about reinforcement learning just basically in a class I was in, and I was like, okay, this is kind of cool. Like I had some idea of how much it would help me in life, but then like a few weeks later, I had an interview and they're like, oh, reinforcement learning, like tell me about that. And it kind of changed my life in more ways than I thought. And so that motivated me to, next time I come up to a class that teaches a hard subject, my Q function is updated because it actually gave me more expected reward more reward than I was expecting to get. And so we need to talk about how do we update this Q function. So, as a baby, maybe we're kind of equipped with a Q function in our own brain that is just random. We have no idea, given some whatever, clumsy baby we are, whatever state we're in, we just take random actions and we have no idea how much reward that's going to give us over our entire life. And obviously, I guess it depends all right, under the assumption that we don't get to live multiple lives, we don't get to just wait till the end of our lives to see, were we correct in all the actions we took. We don't get that luxury of, living as many lives as we want to rebuild that Q function. So what we have to do instead is day by day, we have to be updating this Q function with just a small difference, with the small update, right? I took a class, I had some expected reward, and then it turns out that it was way better than I expected. And so now I can update my Q function in my brain about when I'm in that state again, what action I should take, study hard. So yeah, this day-to-day kind of updating is called temporal difference updating. And in our analogy, the waiting till the end of your life and then updating all your Q functions throughout all your life, that would be called a Markov decision Markov process updates. Markov. Someone's telling me in the chat. MDPs, yeah, Markov decision processes. Yeah, I thought there was a slightly different name, but yeah, okay. So, so obviously we don't want to wait till the end of our life to figure out how good or bad our actions are. We update day by day, and so that can be formally written in this temporal difference update. And so let's talk about that. I don't know which I should approach first. Let me just finish out this first bullet point. So our ultimate goal, right, is to come up with an optimal policy. We talked about that. And so we're kind of going out at a roundabout way, but it turns out the Q function, once we have a Q function, we can use it to come up with our optimal policy pretty simply, because our Q function is, or we can see here, the relationship between the optimal policy and how we use the Q function. So if we had a perfect Q function, if we knew exactly the reward that every action in our life would take under any state, then, and that's called Q prime. You know, if we were the omniscient, that would be like if we were omniscient. Sorry, words are hard. If we knew everything, we would have this ultimate Q function that would tell us for sure the exact reward of taking some action in some state. And then we would just have to look at all the possible actions we could take, and whatever action brings us the most reward, that's the action that we choose for the policy. Unfortunately, we don't know that, and so we often we don't have this Q star because we don't know everything. We only have a Q, you know, because we don't have like this ultimate knowledge of everything. We only have like an idea of what actions we'll take. So we don't always operate according to the optimal policy. And I think that's true for all of us. We can look back at our life and be like, well, that was a really dumb decision. But now I can look back and I can actually update the Q function in my brain. And so next time when I come across that state, I can take an action which actually gets me a better reward because my Q function is closer to this optimal. But we probably won't ever actually find an optimal policy, right? Or optimal Q function, because we'll never know anything. But hey, we do the best we can, you know? We're trying to make it by. So now I can talk about the temporal difference. Okay, how we update this Q function in our brain or in the computer is, you know, I told you it could be, let's think of it as a matrix. That's just the simplest way to think about it. And so, you know, the state and action are like indices in this matrix. And so each entry in the Q matrix should represent the expected lifetime reward of taking that action in that state. That's what it should. That's if Q was Q prime, that's what it would represent. However, Q is not Q prime. Q is an approximation of Q prime. So we have to continually update Q, like in our life, right? And so how we do that is I'm going to make some decision today. I think we can go with the same example we've been using about, you know, I went to that reinforcement learning class, okay? So say this is me sitting in that reinforcement learning class. And I decided to, you know, I was sitting in that reinforcement learning class. I decided to study hard. That was the action I took. And I had some idea of the reward that would give me. However, what ended up happening is that I'm sorry, actually this isn't the best formulation, but I'll try to go with it. I don't like this formulation as much. What ended up happening, so I took a specific action, and what that did is that put me in some new state. So I studied hard, and that put me in some new state of some new knowledge I had. And so that's that S prime. And so I'm going to update that reward that I thought I would have from studying hard in that reinforcement learning class by taking some weight of, you know, that previous experience, but then appending to it some new update of the difference in the expected reward that I had. So this term is the difference between what I expected my reward would be and what my reward actually was. And let me try to convince you of that. So this QSNA was the reward I thought I would have from studying hard in that reinforcement learning class. But when I did that and I studied hard in that reinforcement learning class, I got some reward function, which was getting that internship. And then I also have my expected reward for, now that I have this new knowledge, some new action that I'll take. Sorry, this is kind of falling apart a little because I just realized I don't like this formulation as much. But the idea here is, and it's just not super clear in the math, but the idea here is this is the difference between the reward I was expecting to get and then the reward I actually got. The reward I actually got from studying hard in that class was a lot better, right? So this difference is actually kind of big. So this alpha parameter is like the learning rate, and that's how much importance we put to as we learn in life. And a baby might set the learning rate to actually like really high, because every new experience they have completely, is a paradigm shift for them. It completely revolutionizes their world. And so they're learning very, very quickly. But as you get older and older, you start to realize that the cue function I have in my brain is pretty well set, because it's based on a lot of experience. So I might want to lower my learning rate throughout my life, so that when new experience comes about, I'm still going to pay a little bit of attention to it, but really not as much. And so some algorithms that we look at start to like adjust that learning rate through the learning process. And this gamma parameter that you'll see show up a lot is the discount factor. And it comes from this idea of, so we've been talking about how we want to find the action which optimizes the reward for the rest of our life. Well, that's true, but there's a slight caveat that rewards later on in life don't matter as much as rewards, right now. So if I set this gamma to 0, meaning that I don't care at all about future rewards, then I think it can be shown that this formulation actually reduces to a greedy approach, and you would not be at this workshop tonight. But if this is set to 1, then you're always gonna like be very forward-minded and really care about future rewards, and you're gonna be considering that. So just kind of hopefully intuitive way to think about setting gamma is how stochastic is your environment. If you think that life is completely crazy and you have no idea what's going to happen tomorrow, absolutely no control, and it's just kind of a free-for-all, then you'd probably want to only care about your pleasure right now, right? So you'd set gamma to 0. But if you think that life is more or less deterministic, then you want to set gamma to near 1, because your estimate of your reward in the future is near certain. In practice, by the way, gamma is normally set between 0.9 and 1. It's not really ever set below 0.9. Okay. Basically means we update the estimate for the expected reward in a state. Taking action in our current state, getting to some next state. Yeah, I think we talked about that. All right. One last thing we need to talk about with coming up with this method is this exploration-exploitation trade-off. That's really big in reinforcement learning. A baby, notice, they might have some idea of what they think would get them future reward, but a baby has a very bad cue function, right? And so we'd actually want that baby to be as exploratory as possible, and not just, like, if you will, exploit their current cue function. Exploiting means using. So if a baby, took one example out of life and then just like acted according to that, that's probably not they probably still don't have a very well-developed cue function. And so they'd actually you would want a baby to do more exploration. But then once that baby grows up and becomes a grandma or grandpa, you don't want them skydiving and traveling the world in 20 days. So you don't want them to like explore as much, right? Like you kind of want them to, they probably have a pretty good idea of their cue function, and so you just want them to explore that or exploit that cue function. So we need to define this formally, and we do that with the cue method. We do that according to what's called like an epsilon greedy policy is what we call it. And the idea with epsilon is that we set some epsilon, and then we generate a random number. So epsilon goes between like 0 and 1, and then we generate a 0 number between 0 and 1. And if that random number is less than epsilon, then we just take a random action. And then as we like get older, as we grow in our training, we reduce the epsilon so that we're less likely to take random actions. So yeah, that's kind of what happens there. I'm about to go to the official algorithm right here, but before I do that, I want to see if there's any question. Ooh, skydiving is fun. I like that. I have not been skydiving, but it sounds really fun. Where did you go? Would you go skydiving? Or are you just saying it seems fun? Your Q function says that it would be fun to skydive. Ooh, in Arkansas. Okay. Would you say that your Q function updated after you went skydiving, aka was your experience? Oh, you went and then you broke your leg. Okay, all right, that's interesting. From skydiving? Oh,
No, it wasn't from skydiving. I decided to take up gymnastics and then I broke my leg.
oh, so it's unrelated to skydiving.
Well, it was related because my Q function was updated, so I indulged in risky behavior of taking up gymnastics. So.
Oh, because you went skydiving and then you're like,
Exactly.
Okay, yeah. But would you do it again?
Yeah, definitely.
All right. So your reward function is still positive. Still.
Yeah, we hope most people's are.
Yeah. Yeah. We hope your done signal doesn't equal true. All right. All right. That's awesome.
So there's just like a 5-minute sort of warning to leave time for the feedback and the Q&A.
All right. Oh no. All right. Thanks, Felicia. Do like, I don't know if I'm going slow. Let's see, I only have 5 more minutes, so I would ask again if I'm going at a good pace, but I guess it wouldn't affect much right now. I want to finish up, I guess, with the Q learning algorithm, which should be pretty simple because we talked about it all. Talk about policy optimization, but I'm going to spend a little bit of time talking about, where do you go from here? How do you use what you've learned? All right. Okay, so the algorithm is really what we talked about. If it doesn't make sense to you, just kind of don't pay attention to it because you already know the algorithm. So this just formalizes it, but it might complicate things for you. The idea is this: look at an episode, initialize some state space. So that was kind of like where we did like an environment.reset, and then for each step of the episode, so AKA until we're done with the episode, until we pass away in life. Choose an action, given some state using a policy derived from Q. And we talked above about how we derive that policy from Q. But then there's also that epsilon greedy approach that kind of puts some exploration in there. So then we take action A in our environment, we observe some reward and some new state, and then we update our Q function with that. I think this is called the Bellman. It's either called the Bellman operator or the backup. I think it's actually called the backup formally. Maybe someone in the chat knows, but the Bellman. This is the Bellman. Okay. I get them confused sometimes. So yeah, we update the Q function and then we update our state. So we move to the new state until we've enjoyed a good life. And now it's time to pass it. And yeah, that's how we live the optimal life. So you didn't know this was actually a self-help lesson. Yeah. All right, well that's the Q learning, and hopefully that's a good introduction. There's also the approach of optimizing. So I can't actually get into off policy versus on policy right now. There's also the approach of just optimizing the policy directly using gradient descent, which maybe was the first thing you thought of, and maybe you were thinking like, why don't we just do that in the first place? If we want to optimize the parameters, why don't we just do gradient ascent on the expected value of the rewards given some parameter values? Well, you can do that, and that's actually how a lot of algorithms work, but the math is a lot deeper than what we just did, and involves a lot of probability theory and proofs and calculus, and I'm not sure if we could have gotten through it in that way. But the theory is here, And I will say I read this at the beginning of the summer and had no idea what it was talking about. And but I've been rereading it a couple times, and you know, it comes to you in stages. So maybe give it an initial read over, and then come back to it over the next few weeks or months. All right. Here is kind of the Q function in code. And here you can kind of see the epsilon greedy playing out. If, you know, like we said, we take some random action with some probability, or otherwise we just take the action which maximizes the Q function for the given state. And if you run this code, actually, I don't think it will work right now. I just copied and pasted it from some other work I've done, and I did not have time to get it to work. Yeah, so y'all probably want to talk about the stock challenge, but I'm going to just open that up to questions if you have any specific questions about the stock challenge. Or this, or whatever you want to talk about. We have 20 more minutes, so trying to leave.
Yeah, I left the room the room open until like 11. But for now, should I send out the feedback survey?
Yeah, thanks. Yeah, Felicia just posted this feedback survey that it's literally like 3 questions and should take 30 seconds and would super help us. If you would please fill that out. I literally just asked, how hard was this class? And was it applicable, useful to you? Okay.
And then after y'all fill that out, feel free to like type questions in the chat or just unmute and ask.
Okay, the question was from Jeremy. Is there a simple hello world reinforcement learning project that you would recommend for people who want to explore reinforcement learning more? Yeah, absolutely. So the gym environment makes getting started in reinforcement learning really easy. So we talked about here how we can define we've talked about how we define our own environment, but gym actually comes with a lot of pre-built environments. So let me open that up. Gym environments. So gym comes with a bunch of environments that handle all like the physics and everything, so you don't have to worry about that. And they're all have exactly the same interface that we've talked about here. So a fun one, the ones I got started on are Cartpool and Mountain Car. So let's look at Cartpool. So what happens with Cartpool is it's a continuous action space that tells you, I think, the degree of the pool and the velocity, the lateral velocity that you're moving at. And so that's the state space. And then the action that you have to take is, do I move the cart to the left or the right along this pool? And so that I can balance the beam, right? And so your reward would be +1, like kind of like the environment we looked at, +1 if the action you took doesn't result in a failure, or -1 if it results in a failure. Actually, a really cool YouTube video about people. Oh, maybe showing my YouTube isn't recommended. Okay, so Cartpool real life maybe. Yeah, this is the one I wanted to show you. So this is like where someone played in the simulated environment and then used their algorithm in real world. So this is the Cartpool, but in real world. So notice how it's going to show you at the beginning it's pretty dumb, takes random actions. Oh, I can't get the pool up. I'm going to annotate it for you. All right. when you watch these things, when you watch your algorithms train, you really feel like you're like a proud mom or dad, like when it's working, you're like, come on, you got this. And you kind of just sit there. Oh, yeah, come on. Oh, you're getting better. Yeah, you're doing so good. That's trial 3, you know. So the reward function is, I'm not sure exactly what reward function is. Sorry, this maybe isn't the best use of time, but it's just really fun to watch. Oh, trial 4. So it learned how to get the pool up, but it doesn't know how to keep it up. All right, I'll fast forward. Cool. I don't know if I can. All right, let's just look at the. It's so funny. Okay, I know. I love it. I love it. This is all I do. This is all you do as a reinforcement learning engineer. You just like watch these things and you're just like, oh, come on, you got this. You're really rooting for it. You want the best for it. You know, if I never have kids, this is all I need. I just need like a good, like, feel, oh, I'm a proud. Oh, come on, oh, I'm so close. Okay. I'm sorry. We're gonna finish. But let's look at this. I think this is towards the end of learning. Oh, look at that. It's able to keep it up. That's pretty cool. That's pretty cool. All right. Anyways, that's a real life application to show you that this stuff is actually pretty cool. So how would you use this? Well, it's pretty simple. And I'm going to share this notebook with you, which is getting started in reinforcement learning. And it allows you, so this is like the environment, right? So this is it visualizing, and this is like a simulated. So when it kind of glitches and resets, that's because it's like the pool was tipping too much. So these pre-built environments, like what I just showed you, and any of the other pre-built environments, you can look at Mountain Car or any of the others, all have a very easy way of building them. You just do make cart pool, and that creates the environment. So you don't have to like define the environment yourself. It's already been defined for you. And then there's this library called stable baselines that it makes reinforcement learning honestly almost too easy, because everything we've talked about. So we talked about a queue network, right? A queue algorithm. So you can do just DQN. That's actually a deep queue network, and you just pass it the environment. And so now this is your model or your agent. And so you can actually, so this goes through some code. I'll share this link. This goes through some code to evaluate your agent, and then you pretty much just, you know, make the environment, you can evaluate your agent, and then you can actually like train your agent very easily by just doing .learn. So maybe this isn't the best way to get started, but it's a very awesome way to, it just makes reinforcement learning like really easy. And any of the more advanced models too that we didn't get time to talk about, you can easily import them from stable baselines. So like PPO2 is one I've used a lot, and it takes a lot to implement, but you can just import it like that. So yeah, I definitely recommend checking out stable baselines, especially, yeah, if you just want to get started right away. And this goes through how to use stable baselines. I will send a link in the Discord after this too about some other like beginner resources. But yeah, just start with, I would start with the cartpool environment and just play around with that environment a lot. You know, remember what I said, try to create a rule-based algorithm for cartpool. You can maybe think of a rule base that says, you know, if the state is like too far this way, then move left, and so on. And just start playing with it like that. And then, oh yes, can you tell me some simple applications of reinforcement learning in the industry? By simple, I mean the type of project that can be built by an individual. I mean, yeah, I just showed you one, right? Like the beam balancing. What's really cool about that, so let's think about like other ways that could be done, that beam balancing. We could like create a rule-based algorithm, a rule-based type policy, which is possible for something that simple, but it's still kind of hard. You'll see as you try to create a rule-based environment, there's all these like edge cases that you need to consider. And so if we were to try to create a role-based agent that kept that pool up, it would be kind of hard. The other way we could do it is through supervised learning. And so for supervised learning, you pretty much need a data set that is just like the state that you're in and the action that you took. So what you need is pretty much like a human controller that like is trying to keep that pull up. And then that creates a data set that you can feed into a supervised learning model. But the problem with that is that you actually need a lot of supervised learning, and there's problems with generalization and stuff. And so reinforcement learning kind of revolutionized the field of robotics by being able to create like expert controllers without any human intervention. Like the computer just learns how to do it. So like my field of research is in using reinforcement learning for self-driving cars. And it's a very hot area of research that I definitely think will be incorporated in self-driving cars in the near future. Other form, I mean, reinforcement learning is used everywhere. Mostly in research right now still though. It's a pretty researchy type topic. But you know, stock prediction, let's see where else. It's really good in games. Oh yeah. That's where like reinforcement learning has found like its most success, is it's actually like beating humans in like very complex games such as like Dota. And so you can actually create a like agent that plays a game against you. And that's, you know, a fun way to maybe a fun starter project is think of like a simple game and then try to train like a reinforcement learning agent to play that game. All right, the next question is reinforced learning more accurate than supervised learning for most applications at this point? What are the drawbacks of reinforcement learning versus unsupervised and supervised? Okay, good question. More accurate. I would say the simple answer to that is no, it's not more accurate. Because reinforcement learning, one of the biggest drawbacks of it is that state spaces are generally very, very large, and action spaces are generally very, very large. And so think of that Q matrix as like your action space approaches a continuous action space. That Q matrix grows exponentially, right? Or I guess at least polynomially. And so it becomes very hard to approximate that Q matrix using like supervised learning. And so a lot of the research in reinforcement learning is how do we make, with as few samples as possible, you know, as few days in our life as possible, how can we make a good Q function or a good policy? And that's actually really hard to do. So I would say if you could do supervised learning, it might be preferable to reinforcement learning. But now I'll talk about, so that's a drawback of reinforcement learning over at least supervised. Another drawback of reinforcement learning is that we actually have to define a reward function. And that's not, sometimes it's easy, like in the environments we've talked about, you know, it's pretty obvious, like, okay, if we lose, it's -1 point. If we make a successful move, that's +1 point. But in a lot of times, it's not so easy to describe a reward function. And it's very like hand wavy. And honestly, I hate this about reinforcement learning. Like I use reinforcement learning for self-driving cars. And in self-driving cars, you have all sorts of things you have to consider. You know, are we respecting road traffic? Are we not colliding into other people and cars? Are we, you know, making this a comfortable ride? Are we making it an efficient ride? And there's all these things we have to consider. And so the engineer has to design this very complex reward function that is pretty hand wavy. And, you know, honestly, more time than I'd like to admit has been spent just changing like the reward function. And it's just like, it's pretty arbitrary how you define a reward function. So I don't like that about reinforcement learning. And I think it's something that needs improved. There's a really cool field of research called inverse reinforcement learning that actually tries to learn the reward function from a supervised model. Yeah, so that's some of the drawbacks of reinforcement learning. The main advantages of reinforcement learning is that, at least in model 3, we don't need a model of the environment. One big thing. Another big thing is we don't need copious amounts of data. For, you know, for self-driving cars, there's a lot of research that uses supervised learning to say, learn how to steer the wheel, but they have to have humans drive for hundreds of hours in various environments. And that's very expensive data to obtain and stuff. And so reinforcement learning doesn't need any of that data. Another advantage of reinforcement learning, say for self-driving, is a reinforcement learning agent is able to drive the car in a simulation, into a lot of like crash scenarios. And so it's able to learn how to recover itself from near crash scenarios. Whereas like if we wanted to train it with supervised learning, we wouldn't ask a human to go and crash into a bunch of things and to like, go really close to a crash and then steer away. So if we were trying to get a human data set and then use that to self-drive a car, then when that car drives, it may not be able to control itself in those near crash situations. So that's another reason why reinforcement learning is good. Okay, so we have a question. Is reinforcement learning, oh, no. Okay, if there's time. How long do the models take to train? Yeah, that's a very good question. And that kind of touches on what I was talking about with the, the state space blows up very quickly and the action space blows up very quickly. And so learning that Q function for more advanced or more complex state and action spaces is very hard. And so it can take a long time to train reinforcement learning algorithms. I mean, most of my experiments are pretty small, and so they might take like 30 minutes or something. But in like cutting edge research papers, you'll see them talk about how their model took, 2 or 3 days to train, up to a couple weeks to train. This is on like the most advanced computers out there. So yeah, I mean, just in machine learning in general, that's one of my biggest complaints is you spend a lot of time adjusting hyperparameters and then just clicking retrain and then, having to wait a day and hope it went well. And, oh, it didn't go too well. I'm try different hyperparameters. So yeah, they can take a while to train. But most of my experiments, I run small experiments, can take like 30 minutes or so. But I've run experiments that, I have to run overnight, like 8 hours. And so that's and you guys are seriously troopers. Yeah, I'm just so thankful y'all are here, and it's just been a true pleasure to be able to talk to y'all tonight. I know we didn't get much into the challenge, but yeah, I didn't get many questions about it, so maybe it wasn't something y'all were needing at this moment. But feel free to reach out, and I'm really happy to talk to you more about this.